Welcome to month 3 of the DevOps Engineer track. Last month, you hardened your Docker images, multi-stage builds, non-root users, Trivy vulnerability gates, signed images in Harbor. You know how to build and secure a container. Today, you learn how to deploy it properly at scale. This session is where containers meet production. Kubernetes is the orchestration layer that takes everything you packaged last month and runs it reliably, self-healing, scalable, with controlled rollouts. By the end of today, you will have a running BISTEC Mart stack on Kubernetes, plus a Helm chart that deploys it with a single command across stage and production. Before we look at any YAML, let us anchor this in a problem. Imagine a BISTEC Mart running on a single VM with Docker Compose. That works until it does not. First, no self-healing. If the catalog container crashes at 2 a.m., it stays down until someone restarts it manually. With Kubernetes, the control plane notices the pod is gone and schedules a replacement within seconds. Second, manual scaling. Traffic spikes on the storefront. With Compose, you SSH in, add containers, figure out load balancer entries. With Kubernetes, you change a replica count, and the scheduler places new pods on available nodes automatically. Third, no rollout control. Updating with Compose means downtime. With Kubernetes rolling updates, pods are replaced one at a time, gated by readiness probes. If the new version is broken, the rollout pauses automatically. The key mental model for this entire session, you declare the desired state, and the Kubernetes control loop continuously reconciles actual state toward it. This is not a one-shot command. It is a declaration, maintained forever. Let us walk the chain from the bottom up. Understanding why each layer exists is more important than memorizing the API. At the bottom is the pod, the smallest schedulable unit in Kubernetes. A pod contains one or more containers that share a network namespace and storage volumes. If you create a bare pod and it crashes, it is gone. No controller watches it. So in production, you almost never create pods directly. The replica set sits above the pod. Its job is to ensure a specified number of identical pods are running at all times. It watches with a label selector loop, counts pods matching its selector, and creates or deletes pods to match the desired count. If a pod crashes or is evicted, the replica set creates a replacement. This is self-healing, but the replica set has no concept of rolling updates. That is the deployment's job. The deployment owns one or more replica sets. When you change the image tag in a deployment spec, the deployment controller creates a new replica set with the new image and scales the old one down incrementally. It tracks revision history. Kubectl rollout undo restores the previous replica set. The mental model. You write a deployment. Deployment creates a replica set. The replica set creates pods. You almost never interact with replica sets directly. Deployments handle the majority of workloads, stateless services, APIs, workers. But 4 other types solve specific problems that deployments cannot address well. Stateful set is for workloads that need stable identity. Pods in a stateful set get predictable names: Postgres 0, Postgres 1, Postgres 2. They start and stop in order. Each pod gets its own persistent volume claim. If Postgres 0 restarts, it reattaches to the same storage it had before. Use stateful set for databases and anything where which pod you are matters. Daemon set places exactly one pod on every eligible node. As nodes join the cluster, the daemon set scheduler adds a pod automatically. This is the right pattern for node-level infrastructure, log collectors, monitoring agents, CNI plugins. Job runs pods to completion. Once the required number of pods succeed, the job is done. Classic uses: database migrations before a deployment, one-shot batch processing. Cron job creates a job on a cron schedule. Note that the cron job controller has roughly plus or minus 30 seconds of scheduling jitter. Do not depend on it for sub-minute precision. The decision question: does this workload need to keep running? Use deployment or stateful set. Does it need to run to completion? Use job or cron job. Does each node need exactly one? Use daemon set. Services are how pods find each other, and how the outside world reaches your application. The type you choose depends on who needs to reach the pods and from where. Cluster IP is the default and most common type. It creates a stable virtual IP inside the cluster. Traffic to that IP is load balanced across healthy pods matching the selector. Cluster IP is not reachable from outside the cluster. That is intentional. Node port maps a port on every node's IP to the service. It is reachable externally by hitting any node IP on a port in the 3000 to 327.667 range. Fine for lab access, but avoid in production. The port numbers are ugly, and you have to maintain which node IP is healthy. Load balancer provisions a cloud load balancer. This is how you expose a non-HTTP service externally in production. For HTTP services, Ingress is usually the better choice because one Ingress controller can handle many virtual hosts. External name maps a cluster DNS name to an external FQDN. Use this when migrating a service out of the cluster, and you want internal consumers. Keep using the same hostname during the transition. Ingress is not a service type. It is a separate resource. An Ingress controller watches Ingress resources and configures HTTP routing rules. In our lab, NGINX handles this. BISTEC Mart local API routes to the catalog cluster IP service, and BISTEC Mart local routes to the storefront. TLS termination happens at the Ingress controller. Configuration and credentials should not be baked into container images. Config maps hold non-sensitive configuration. Secrets hold sensitive values. Both inject config into pods without rebuilding images. A config map can store individual key value pairs like app, env, and log level, or it can store a whole file. When mounted as a file, the pod sees the file at the specified path. When mounted as envvars, the pod sees individual environment variables. Secrets look almost identical. When you use string data, kubectl base64 encodes the values before storing them. Important: secrets are not encrypted at rest by default. etcd stores them as base64, which is encoding, not encryption. Anyone with etcd access can read them. There are two mounting strategies. Envvars are simple and work with any application. The risk: envvars are visible in process listings and in crash logs. File mounts have one useful property. When the config map is updated, the file in the pod updates, eventually without a pod restart. Two things to never forget. Neither config map nor secret is encrypted at rest by default. And never commit secret YAML with real values to Git. Use sealed secrets or an external secrets operator for production. Probes are how Kubernetes knows whether your container is healthy, ready for traffic, and finished starting. Getting them wrong is one of the most common causes of production incidents. Liveness probe. Kubernetes restarts the container when this fails. If you set the liveness probe path to health, but your health endpoint is actually at healths, every probe fails, every container restarts, and you have a crash loop backoff with a perfectly healthy application. The liveness probe should only check whether the process is stuck or deadlocked, not whether it is warm or connected to dependencies. Readiness probe. Kubernetes removes the pod from service endpoints when this fails. Traffic stops going to that pod. If you forget a readiness probe on a slow-starting app, traffic hits the pod while the application is still loading and users see 500 errors. The readiness probe path should verify that the app can actually handle requests. Startup probe disables the liveness probe until it succeeds. Without a startup probe on a slow-starting pod, the liveness probe fires during startup, kills the container, and it never finishes starting. A failure threshold of 30 with a period seconds of 10 gives the app up to 5 minutes to start before the liveness probe activates. The Catalog FastAPI app uses ATP-GET on health for liveness and startup, and ready for readiness. The ready endpoint checks that the database connection pool is healthy. The health endpoint just confirms the process is responding. Resource requests and limits are how you communicate resource needs to the Kubernetes scheduler, and how the kernel enforces ceilings on running containers. A request is a reservation. The scheduler adds up all requests on a node and only places a pod there if the node has enough uncommitted capacity. Requests do not cap actual usage. A pod can use more than it requested if the node has spare capacity. A limit is the ceiling. For CPU, when a container exceeds its limit, the kernel throttles it. The container does not crash, it just gets slower, latency spikes. For memory, when a container exceeds its limit, the kernel sends sigkill immediately. No graceful shutdown. Killed appears in kubectl describe pod. Kubernetes assigns each pod a quality of service class based on how requests and limits are configured. Guaranteed means every container has requests equal to limits for both CPU and memory. Highest priority, last to be evicted. Burstable means requests are set but lower than limits. Most workloads fall here. Best effort means no requests or limits at all. First to be evicted, always. Never run production workloads with no resource configuration. Always set both requests and limits explicitly. A pod with no resource configuration is ephemeral at the cluster's convenience. Now you build. For the first lab block, you will author bare YAML manifests for the catalog service. No Helm yet. Raw Kubernetes objects. This is intentional. Understanding what Helm generates requires understanding what the raw objects look like. Step 1. Author a deployment for catalog with 2 replicas and a cluster-IP service. Apply it. Verify the pods are running. And reach the service via kubectl port forward. You should be able to hit the API docs from your browser. Step 2. Add the Ingress resource. Configure your Ingress to route BISTEC Mart not local API to the catalog service. After applying curl HTTP, BISTEC Mart local API from your terminal. Step 3. Add all 3 probes: startup, liveness, and readiness. Then deliberately break one. Change the liveness path to something that does not exist and watch what happens. Read the event. Fix it. Step 4. Add requests and limits. Then trigger an kill by setting the memory limit very low. Read the postmortem in kubectl describe pod. 2 habits to build right now. Read kubectl describe pod before asking for help, and read kubectl get events. Most Kubernetes problems are diagnosed in those 2 outputs. Part 2 builds on Part 1. You have a running catalog deployment. Now you extract configuration into config maps and secrets, and add Postgres as a stateful set with persistent storage. Step 5. Take the environment variables currently hard-coded in your deployment and move them into a config map. Do this twice, once using envfrom to get all values as envvars, and once mounting the config map as a file. Exec into the pod and verify both approaches work. Step 6. Take the database password out of the deployment YAML and into a secret. Reference it via envfrom in the catalog deployment. Verify that the password is available in the pod environment. Step 7. Deploy Postgres as a stateful set. The service name field in the stateful set spec must match a headless service with cluster-IP. None. Create the service first. The volume claim templates block creates a 1 GB PVC called pg data for Postgres 0 automatically, mounted at var lib PostgreSQL data. Step 8. The payoff. Once Postgres 0 is running, exec in and create a database and a table. Delete the pod. Watch it come back. Exec in again. Your data is still there. This is the fundamental reason stateful set exists. Storage outlives the pod. Think of Helm as the package manager for Kubernetes. npm packages Node GJOI's libraries. Helm packages Kubernetes applications. A Helm chart is a collection of YAML templates with a values file that makes them configurable. Instead of hard-coding image tags and replica counts, you parameterize them. The chart skeleton has a clear structure. Chart YAML is the manifest, name, version, app version. Values YAML contains default values. Environment-specific files like values dev YAML and values prod YAML contain overrides. The templates directory contains your Kubernetes YAML with Go template syntax for variable substitution. Run Helm create BISTEC Mart to scaffold the chart. You will get a generated directory with templates for deployment, a service, an HPA, a service account, and tests. Delete most of it. The generated boilerplate adds noise. Keep only what you understand. If you cannot explain what a file does, delete it and see if Helm install still works. 2 patterns in helpers.tpl are worth building immediately. Define your chart name and labels as named templates and use them everywhere. If you copy-paste the release name string across 5 templates and then rename the chart, all 5 break. The helper makes it consistent in one place. This slide shows the values pattern in practice. Values YAML holds safe defaults, latest image tag, 1 replica, conservative resource limits. The prod values file overrides what needs to be different in production. A pinned image tag, 3 replicas, higher resource limits, and the production hostname. Notice that values prod YAML only specifies the keys it overrides. Helm deep merges the values files. Environment values take precedence over defaults, and anything not mentioned in the override file falls through to the default. You do not repeat the entire value structure in every environment file. 3 deploy patterns you will use constantly. Helm install for first-time installation. Helm upgrade. Install for CI pipelines. It is idempotent, installing if the release does not exist and upgrading if it does. And Helm rollback when a release needs to be reversed. Helm history shows every revision with timestamps and status. Helm rollback BISTEC Mart 2 restores revision 2. Before you upgrade in production, run Helm diff upgrade to see exactly what will change in the cluster. That is a mandatory step before touching a production release. This is the troubleshooting toolkit. When something is broken in a Kubernetes cluster, these 5 commands in order will diagnose the majority of problems you encounter. First, kubectl describe pod. Read the events section at the bottom. Killed, image pull errors, probe failures, scheduling failures, they all appear here. Make this your first reflex. Second, kubectl logs. When a container is in crash loop backoff, the current container might not have logs yet. Previous gets the logs from the last terminated container. Essential for crash loops. Third, kubectl get events sorted by timestamp. When something broke a few minutes ago, and you do not know where to start, this command gives you a timeline. Fourth, kubectl debug. This attaches an ephemeral debug container to a running pod. When your application container has no shell, and minimal production images should not, kubectl debug injects a busybox container running alongside it with access to the shared network namespace. Fifth, kubectl pod containers. This shows live CPU and memory usage per container. When a container is throttled or approaching its memory limit, this shows it. The diagnosis workflow. Check pod state. Read describe events. Read previous logs, exec-in. Crash loop backoff means the container keeps exiting. Killed means the memory limit was hit. Pending means the scheduler could not place the pod. Each state tells you exactly where to look. Now you can deploy and debug. The question is how you update a running application. Your rollout strategy determines what happens to live traffic during a deployment. Rolling update is the default, and the right choice for stateless services like catalog and storefront. Kubernetes replaces pods one at a time. With max unavailable set to 0 and max surge set to 1, no pod is terminated until a healthy replacement is ready, and one extra pod can exist above the desired count during the rollout. The readiness probe gates each step. A new pod only receives traffic after its readiness probe passes. If probes keep failing, the rollout pauses automatically. Kubectl rollout undo reverses it. Recreate terminates all old pods before starting new ones. There is a downtime gap. Use this only when two versions of the application cannot coexist. For example, when a database schema migration is non-backward compatible, acceptable in dev or staging, avoid for customer-facing production services. Blue-green is not a native Kubernetes strategy. You implement it using two deployments and an Ingress backend switch. When the green deployment is fully healthy, you update the Ingress to point to the green service. Rollback is instant. Flip the Ingress back. The cost is double the compute during the transition. For BISTEC Mart catalog in production, rolling updates with proper probes give you zero downtime with no extra resource cost. That is the right starting point. Here is exactly what you are submitting and what you are scored on. Deliverable 1, 25 points. The bare YAML manifests from Part 1, a deployment, a cluster-IP service, and an ingress for the catalog service. Probes and resource limits are required, not optional. A deployment without probes and limits is not production-ready, and the scoring reflects that. Deliverable 2, 20 points. The stateful set and PVC from Part 2, Postgres as a stateful set with a 1 GB PVC, a headless service, and a demonstration that data survives a pod deletion. Screenshots of the before and after, with kubectl get PVC showing the PVC still bound. Deliverable 3, 30 points. The full Helm chart. The chart directory values a YAML with sensible defaults, and dev stage and prod override files. Run Helm history after at least 2 installs to show revision tracking. The 30-point weight signals where to invest your time. Helm is what you will use every day in production. Deliverable 4, 25 points. The probe and resource design document in Markdown. For each workload, document which probe paths and thresholds you chose and why, which COAS class the pod has and why, and the OMKill postmortem from the lab, what you set the limit to, what happened, and what you changed. Common mistake: copying the Helm create boilerplate without understanding or simplifying it. If your chart has files you cannot explain, delete them. Understanding what you need is the point. 6 milestones to complete before month 4. Add a horizontal pod autoscaler for catalog. It uses the metrics server already installed in the lab cluster to scale replicas up when CPU or memory exceeds a threshold. This is where Kubernetes moves from manually managed replica counts to self-managing infrastructure. Replace the generated helpers.tpl with templates that match your team's naming conventions. The generated helpers are generic. Writing your own makes the chart match your organization's standards, the first step toward a real internal chart library. Add a pod disruption budget for catalog. Min available 1 in dev, 50% in prod. This tells Kubernetes that voluntary disruptions, node drains, cluster upgrades, must leave at least one catalog pod running. Add a network policy that restricts Postgres to only accept traffic from pods labeled app, catalog. Even if another pod in the namespace is compromised, it cannot reach your database directly. For reading, the Kubernetes documentation, workloads, services, and storage sections fill in every gap from today. The Helm Best Practices Guide makes your charts production ready. Kubernetes Up and Running by Burns, Beta, and Hightower, chapters 1 through 7, is the canonical text. And install K9s. It will change how you interact with the cluster every day. Take a moment to recognize what you built today. You started this month knowing how to build and secure a container image. You are leaving with a deployed application running on Kubernetes, proper workload structure, service discovery, health probes, resource management, and a packaged Helm chart with multi-environment support. The pod to replica set to deployment chain is in your mental model. You know why each layer exists. Service types are clear. You can pick the right one without hesitation. Probes gate traffic and restarts. You have broken and fixed them yourself. Requests and limits drive scheduling and OOM behavior. You have triggered an OOM kill and read the postmortem. Helm turns raw YAML into a versioned, parameterized package. You have installed, upgraded, and rolled back a release. That is real infrastructure engineering work. Not theory, you built it. Month 4 is infrastructure as code with Terraform and OpenTofu. You built the application layer today. Deployments, services, Helm charts. Next month, you provision the infrastructure that runs it. VPC, node pools, IAM, managed databases. By the end of month 4, you will be able to provision a complete environment, cluster and application from source code. That is the full DevOps stack. See you next month.